Okay, yesterday I asked you guys to graph several different polynomials. We looked at the graphs. We did some of this together. So we kind of started that first one together. Reminders, it was asking you to look at the left. And if I were to put an arrow on the left-hand side of this graph, which way was that arrow headed? And that arrow was headed up. And numbers that are up are positive infinity. The right-hand side, we would have also put an arrow that was up, and that would be positive infinity. And as I do that to all of these, I noticed all of the arrows that I put on here were headed up to positive infinity. It didn't matter if it was on the left-hand side or the right-hand side. And then we were supposed to find a pattern. Now, looking as you can see the top and the bottom of your worksheet there, the pattern obviously is that everything was positive infinity up here. But what was it about the equations at the top that they had in common? Jude? Even exponents. And now as I look through this, they're not, like literally every exponent is not even, but it's the specifically biggest one, right? Because look at that second one. It's got an odd exponent here at the 3 and the 1, but it's our biggest exponents that mattered. So if you look at that, now look at the second row. What's the biggest exponent on all of these? An odd number, right? Our odd number is the biggest exponent, 3, 5, and 7, and look at the difference in how the ends look. When they're odd, our ends are going one of each direction. The left-hand side is headed down to negative infinity, and the right-hand side was headed up to positive infinity on all three of these. It didn't matter what the odd number was, but if it was odd, your left-hand side was headed down to negative infinity, and your right-hand side was headed up to positive infinity. Any questions on that so far? Okay, and then we flipped over to the back side. And the thing that was added on the back side was a negative. Notice that on our equations. So I have one of each. I have an odd exponent, and I have an even exponent, but they now both have a negative in front of them. And what's happening to the graph when we put that negative in front of it? What changed from the front side?
The right side's going down.
The right side was going down instead of the left side on the odd. Okay, so these flip-flopped, right? Now my left side is headed up to positive infinity, and the right side is headed down to negative infinity. And that one just turned upside down, didn't it? Instead of both ends going up for the even, both ends are headed down to negative infinity. There is a mathematical term for what just happened. When we turn a graph upside down, when we flip it over, it's called reflecting it over our x-axis is what's happening when we put that negative up there. For our end behavior, which is what we're looking at right here, we're going to talk about that today, it just turns our end behavior upside down from what the original rule would have been. So what you guys just did is you kind of figured out our rules for our end behavior based off of our biggest exponents. Whether it's even or odd dictates where the ends of our graph are going. Even, they're going the same way. Odd, they're going opposite ways. And then the negative and the positive in front of it, our leading coefficient, changes the graph as well. So that's what we're going to start with today. And what you did is a mathematical concept called end behavior. So if you'll grab wherever you're going to take your notes, today we are focusing on the end behavior part of section 1.3. So to sum up what our exploration worksheet just found for us is really what dictated when we're looking at polynomials, right? Everything we looked at is a polynomial. Polynomial meaning something like an x to the third plus x squared plus x, whatever. That's a polynomial. And all of our end behaviors depended on our biggest exponent and whether it was an even number or an odd number, right? And if it was an even number, the middles kind of did their own thing, but the ends all did the same thing, right? And the ends all headed the same direction if it was even. And if it was even with a positive leading first term, those ends were both going to head up. And if it was even with a negative first term, those ends were both going to head down. And then if we switched it to being an odd biggest exponent, if it was positive, this is where odd, you got to slow down and think about this one. As I read my graph like I read a sentence or a book from left to right, our odd positive is going to increase as we go. So I draw that kind of generic little picture there. so I can think about what the ends look like for an odd positive. If it's odd and it's negative, it's going to reflect that. It's going to decrease as we go to the right, making my left end go up and my right end go down. And those generic ones tell me about all of the end behaviors for anything that falls in those categories. Polynomial with an even, negative, I know what the ends are going to do. Okay? The middle does not matter when we are looking at end behavior. It's all the way on the ends. Now, in math, we have fancy notation for describing looking at the left-hand side of the graph or the left end of the graph or the right end of the graph. So let's talk about how we correctly write what's called limit notation. In limit notation, we abbreviate the word limit to LIM. So this would be a normal size, lowercase LIM. What follows LIM is your function, and you can either just refer to it as like f of x, or you can literally write in the function 3x plus 7, whatever it is, but that follows where you say LIM. Underneath of LIM, it's usually supposed to fit right underneath those three letters, is a little subscript, so smaller than your normal size letters. And it's telling you that we are headed to the left along the x-axis. Well, the left would be headed towards negative infinity. So it says as x heads to negative infinity. This little symbol right here, x heads to negative infinity, says look at the left-hand side of the graph. And then what follows the equal sign is my answer, and your answer is where is the graph going? It is your y values. What are the y values doing as my graph goes to the left? Same thing for our right-hand notation. Starts out with that LIM, something referring to your function, f of x, actually write in the function, whatever you want to do. And then under LIM says as x approaches positive infinity. And again, this little symbol right here is what we look at to see which direction we're looking. And this one says look to the right. And it's going to equal some answer. And that answer is going to be, again, what are our y values doing as we head that direction? One of the little notes you can make for yourself, whether you want to or not, if you go back to that worksheet, those are all sorts of different polynomials, right? Well, did you notice that every single one of our answers was either positive or negative infinity? Is that always going to happen when it's a polynomial? Absolutely. Okay, so when we're looking at a polynomial, and you guys know what that means, right? X squared plus 5x plus 7, something like that. Your answer is an infinity, up or down. It's either going up or it's going down. We will look at some other options, but those are no longer polynomials. Any questions on limit notation, how I could tell if I'm supposed to look at the right or the left-hand side of my picture? All right. So we're going to go ahead and practice this a little bit. It says use the graph of f of x equals x cubed minus 2x squared minus 4x plus 4. So that you don't have to actually put that in your calculators, I'm going to go ahead and just put it up here so you can just copy that onto your notes so you know what the picture looks like. If I had a picture to look at and I was supposed to be describing the end behavior, describe the end behavior means write out that fancy limit notation that we just learned how to write on the last page. Okay? So as I look at this picture right here, my fancy limit notation says the limit of f of x as x approaches negative infinity as I go to the left. As I go to the left, where is my graph going? So I go to the very farthest left, and I see that the arrow is pointing down. So my graph would be headed towards negative infinity. And then I do that again to go to the right. Limit of my function as x approaches positive infinity to the right. Go to the right-hand side of my graph. The very farthest right my graph goes is right here. Where is it pointing? It is pointing up, and up is positive infinity. So this is left, and this says right. Questions? Okay, so match that up to what we talked about at the beginning. Does that match the polynomial? Well, look at your leading term. That would be an odd positive, and odd positives are going to increase as we go to the right. And that's what my ends are doing. The middle twists and turns don't matter on end behavior. Any questions on that? Okay, so now let's try one without. You are not allowed to graph this one. I want us to look just at the function. So you notice I crossed off graph it. If f of x equals negative x to the fifth minus 2x plus 1, describe its end behavior. Okay, so I want you to take a second and look at that function. Write down your fancy notation for end behavior. The concept that we are going through, especially at this moment right here on this example, we are going to revisit this idea multiple times this semester. And later on, we're going to call this our leading term test. But we're looking at our biggest exponent and the number in front of it. And if I flip back a couple pages here, we're talking this thing right here, right? This chart right here, if you know this chart right here, you know polynomials. Because all we do is look at that biggest exponent and decide which category it goes in. Is it even or odd? We look at the signs underneath. Is my leading term positive or negative? Okay, and that tells me what my graph's going to look like. So as we go back to this one, I don't need to see a picture of it. I look at my biggest term. I see that it is an odd number. And I see that it is a negative first term. Odd and negative, I should have my ends going one of each way. Negative tells me it's decreasing as I go to the right. I don't really know what the whole picture looks like, but I know the ends. Left-hand side is going to go up. Right-hand side is going to go down. So my left-hand side goes up to positive infinity. Right-hand side goes down to negative infinity. Any questions on that? So unless it asks me to specifically graph something, I don't even have to look at the picture to know what the ends are going to do. And you can absolutely use that test to figure that out. All right, so now I want you to take a second and talk at your tables. I'm giving you 4 equations for this picture. Figure out which of those equations would actually work for that picture. Option 1, 2, 3, or 4. Okay, now use words to talk at your table about which option it is. Okay, now I'm going to pick different tables, and you guys are going to eliminate options for me. You're not going to tell me what the correct answer is, but you're going to take one out of the running and tell me why you eliminate that as an option. So take a second and decide which ones you could eliminate and why you would throw that out as a possible answer. Why? Get the why part. Yes. Yep. All right, let's go ahead and go with, still working on my names, Kenzie. Your table eliminated which one? And why did you throw that one out? And what would you have expected to see if you had an odd exponent? Yeah, if you guys can see what she's pointing, she's drawing me a picture where the ends are going opposite ways, right? The curvy one where ends go the opposite ways, okay? Good. Brogan, throw out another one, why? And what would you have expected to see if it was positive? Yep, up both ways, or again a curvy one because of the odd exponent. Okay, let's go with Alex. Why? I agree with the even, yeah, and positive first term. And what would you have expected with that positive first term? Table, help him. He's on the right track. I agree. Throw it out. Positive. What? Would have pointed up, right? Would have pointed up with that positive. Completely agree. Which leaves us to the correct answer, right? Correct answer is 4. Needed 2 things. My ends are headed the same way, so I knew my exponent had to be even. The same direction is negative infinity, or down. And so I knew that that negative had to be in front to make the ends head down to negative infinity. Any questions on any of that? Okay, we are not always working with polynomials. Now we're going to talk about how do we do this whole end behavior thing when it's not a polynomial. What about when it looks like a fraction, or math terms, a rational expression, okay? Well, guys, the first step you're going to do is you're going to figure out which category does that rational expression fall into. There are three: big over little over big, or same. Okay, so that's your three options, and it will fall into one of those categories: big over little over big, or same. So how do I decide on that? Well, again, notes for yourself if you need to remember this, but if to decide on that, it is all based off of our biggest exponent, just like we were looking at with our polynomials, our biggest exponent. So big over little is saying that the exponent in the top of my fraction is bigger than the exponent in the bottom of my fraction. For example, something like an x squared over an x. That would be a big over a little. A 2 over a 1. Little over big could look something like x over x squared. But I also want to show you one that tends to catch people a little bit. What about something like 1 over x? That is little over big. Trick question that's not a trick question. What is the exponent on the x that's in the numerator? What is the exponent that's on the x in the numerator? There isn't an x in the numerator. So for me to not write an x in the numerator, its exponent would be a 0. Okay? So yes, it could be there. We would never write x to the 0 in our problem, right? Which is why you don't actually see it. But that's why it does get put in the category of little over big, because it's an x to the 0 over an x to the first, right? And 0 is smaller than 1. Same, again, we would have the same exponent on each of our terms. So it'd be like a 3x squared over a 4x squared. X squared and x squared, same exponent. We would put that in our same category. Okay, so let's talk about the ends of these graphs and why. The first one, you already have the answers. It says as we go to the right, which means I'm plugging in bigger and bigger x values, right? So I'm putting in bigger x numbers into my function. As I put in bigger numbers, think about this. I'm squaring the top one, but just keeping the bottom one the same. So as I put in 10, this becomes 100 over 10. As I put in 100, I square 100. And then I put in a million, and I square a million, right? Do you see how the top of that fraction is growing way faster than the bottom is? Because as I square a million, isn't it a really, really big number? Okay. So as we plug in bigger numbers, the top of this is getting bigger faster than the bottom, and that's why it's going to continue to just become a bigger and bigger number as we go. So it's going to head towards infinity. Now as I go the other direction and I'm plugging in negative numbers, one of those is negative, one of those is positive, which is why it's resulting in a negative answer. So what does this look like visually? Here's an example of what one of these could look like. And again, we don't care what the middle's doing, but on the very far right, this is going to slowly continue to head up to positive infinity. And on the very far left, which would be all the way over there, this is going to continue to head down to negative infinity. Okay? And then with our little over big, think about plugging in bigger and bigger numbers. If I plug in 10, this would be 1/10. As I plug in 100, this would be 1/100th. As I plug in a million, this would be 1/1,000,000th. And if I handed you 1/1,000,000th of a pizza, I just handed you like nothing, right? 1/1,000,000th of a pizza, right? Not much, right? I did not hand you very much. So what's happening is as the bottom is getting bigger faster, it's basically becoming 0 as I plug in really, really big numbers there. And you'll see that both sides are going to flatline at 0. What does a picture of that look like? As it comes along my x-axis, it ends up flatlining right along that line. And it's going to flatline right along my line here. And again, we don't care what's happening in the middle of the picture. It's on the very far right and left. So the very far right is flatlining at 0. The very far left is flatlining at 0. When it is the same, you notice that we would square the x in the top and we square the x in the bottom. It's growing at the same rate. Okay, now this one we'd be able to just simplify out, and it's easier to see here that this would simplify out to just 3/4. That's not always the case, so we can simplify it. But as we plug in really big numbers, it's growing at the same rate, and that ratio will never change, that the top will be 3 and the bottom will be 4. And that ratio of the numbers in front, what it simplifies down to, is the ratio that we're referring to when we say that it limits at the ratio. So mark that for yourself however you need to mark that. The limit is going to equal the numbers in front of your x. The math term for that is the leading coefficients. So the ratio is the leading coefficients. What does that look like in a picture? We would have what will look like a horizontal asymptote at that number, and your graph would flatline here and flatline there right at 3/4. Okay. So before we move on, real quick, on the back side of your worksheet, we added a negative to the front of each of our equations, and what did that change about our graphs? Well, on here, let's just go through that very quickly. What if I were to put negatives? What if I put a negative at the beginning? This first one that is big over little is the only one that is going to change. As you flip that graph over, because that's what a negative does, it reflects it over our x-axis. Now the right-hand side is going to head down to negative infinity, and the left-hand side is going to head up to positive infinity. So these two would flip-flop. If I turn over the other two graphs, reflect them over their x-axis, actually nothing changes about my picture because it's still going to flatline at the same point. Still flatlining at 0 on the right and left. And this one would still flatline up at 3/4. You do. With where the negative is, yeah. We will get into transformations later where if we put the negative, whether it's inside or outside our function, will change whether it goes over the x or y. Okay. Other questions? So when we do rational expressions and behavior, job number 1, categorize. Little over big, big over little are same, and then remember your rule, and that will find your ends for you. So that's what we're going to do here. I know I have a picture for you, but I don't even think you should need it, and actually I think sometimes the picture is a little bit more confusing than just looking at the function itself. So first job is to categorize. Our function is 8x squared minus 3x plus 2 over 2x minus 2. So does it go in our big over little, little over big, or same?
Big over little.
Big over little. Okay, so then all we do is I just go back to that chart. Big over little says my answers are infinities, right? As I go to the right, it's going to go up to positive infinity. As I go to the left, it's going to go to negative infinity. Be careful of the order that they're written here. Left is written first on my page up here. So as I go to the left, which would be this guy right here, it's going to slowly continue down to negative infinity. As I go to the right side, it's going to continue up to positive infinity, big over little. Yep, exponents, the biggest exponent on our variables, yep. Very good. Questions on that?
So it's not always going to be the first.
It wouldn't always be the first one, as long as if it's written in standard form, it's usually at the beginning. I will tell you, make sure you scan through, because I think on your assignment there's a couple that'll put them out of order, just to make sure that you're paying attention. All right, next one. F of x equals 1 over x minus 2. We kind of already talked about this situation, but which category does that fall in? Big over little, little over big, or same? Little over big, because again, no x means that its exponent is 0, right? There's an x to the 0 over an x to the first, which would put it in the category of little over big. And again, right now we can just go back to our chart and say, okay, well, what are our end behaviors for little over big? What's happening when the bottom of my fraction is growing faster? Well, it's going to essentially become the number 0 on both the left and the right. And again, I like tying this to our visual because eventually this is going to mean something to us. But can you see how it's flatlining at 0, at a y value of 0 and a y value of 0 on both ends? Questions? Okay, let's look at our last category here. 3x plus 1 over x minus 2. Okay, so again, we categorize little over big, big over little, or same? same. X to the first over x to the first. Start with the exponents, right? 1 over 1 is a same. Our rule says look at the ratio, and you have to remind yourself what that means. It's the ratio of the leading coefficients, the number sitting in front of x. If there is no number sitting in front of x, it is 1. So 3 over 1 simplifies, and you always just then simplify that fraction, and that simplifies down to 3. And again, as I look at my picture, here's a y value of 3. Can you see how that one is flatlining as we go further and further to the right and left? It's going to end up flatlining and getting really close to 3 on both ends. Okay. The next two we're going to kind of just fly through here just to look at, but there's one thing I want to talk about on this next problem. Actually, there's two things I want to talk about on this next problem. We can quickly categorize little over big, big over little, or same. Little over big. Okay, so again, I know my rule now. When we are looking at a little over big, says that my left-hand limit is going to be 0, that my right-hand limit is going to be 0, and I want to talk about this before we move on. If your answer is the same for both, there is actually a notation that you can use to speed up this process. I do not have to write these separately if I get the same answer. And if I get the same answer, I can combine it and say that the limit of our function as x goes both directions, positive and negative infinity, equals 0. Now I can only do that if the answer would be the same on both ends, but I don't have to write it twice. Okay, so we can combine it down. The other things I want to talk about on this one are this. This graph is super busy, and there's a ton of stuff going on all in the middle of this, right? We've got like different pieces, and it's kind of breaking up and heading down and all over the place, and I don't care. None of this matters when doing end behavior. Do not be distracted by the middles of the graph. People get distracted by what's going on in the middle. It could write out your name. It could draw you a heart. It can do all of that. It doesn't matter. That's not the ends of the graph. The ends of the graph, I have to go all the way, and it's just this arrow right here, or just this arrow right here, and what is that doing? What y value is it going to? The last thing I want to talk about on this one is the fact that some people want to simplify this one. And does that impact which category it would fall in as far as little over big, big over little, or same? The way this one is written, actually, it doesn't simplify, but I do want to point out, sometimes they will hand it to you in the factored form. Does that change what it is? Not at all. I need to think again, if I were to multiply this out, what would be my biggest exponent? But do you see if I wrote it like this, how a lot of people make the mistake and say that it is a same over same? Because it kind of looks like an x to the first over an x to the first. Okay, so what if I did change the problem? This is not what the problem was, but what if I changed it so that it did simplify? It was a little over big. I factored it out. I'm going to simplify it. It gets down to a 1 over x plus 1. Now which category is it? Still little over big. So just because I simplify it, will it change categories? Never. It will never change categories when you simplify. So don't worry about that part of it. The only thing I would worry about is if it is factored, we need to think about the unfactored version to help you categorize. Okay? Questions on that? All right, the next one I'm going to super fly past. 2x minus 1, 3x plus 2, little over big, big over little, or same. Same. Our answer then, leading coefficients, 2/3. And again, because it is the exact same on both sides, I can put both ways plus and minus infinity, 2/3. All right. Last topic I want to talk about today is what's called your intermediate value theorem. Okay, you don't need to write that whole thing at the top, just the purple. Intermediate value theorem. The thing at the top is saying this: if a function is continuous, you can approximate the location of its zeros by using the intermediate value theorem. And while you guys are writing down that phrase, let me tell you a little about what that means. We learned what continuous means. I can trace my whole graph without ever picking up my pencil. And since I never pick up my pencil, I know that if one of my answers is a negative numbers being down here, right? So if one of my answers was a negative number, and one of my answers was a positive number, and my graph is continuous. As I go from that point to connect my negative number to my positive number, I have to hit my x-axis, right? I have to. There's no other way to get from a negative up to a positive other than going through the x-axis, or vice versa. Going from a positive number down to a negative number, I have to hit my x-axis. So using that idea, I can tell you approximately where the zeros are in our picture, or where it's hitting our x-axis. So let me give you a sample, and this one's pretty much done for us, and then we'll look at actually creating one from scratch here. But it says determine between which consecutive integers the real zeros. So between which numbers we are finding where it hits our x-axis. They give us the function f of x equals x cubed plus 2x plus 5, and then they give us an interval to look at. So these are the x's they want us to test out, from -2 up to 2. There's a table drawn for us. That's something you're going to create on the next page. So let me tell you how they created this table. The interval that they give us gives you the x's that you see listed here. -2, -1, 0, 1, and 2 are the x's that go from -2 up to +2. This right here is your answers when you plug those x's into your function. Okay, so as I go plug this one, put a -2 in, evaluate for this for -2, we get -7. Put a -1 in there, we evaluate it, we get 2, etc. Okay, that's creating the table. Now answering the question, where are the zeros? Where is it going to hit my x-axis? What we are looking for is our answers that switch signs. So if I look at the signs of my answers, we've got a negative number, a positive number, positive, positive, positive. We only switch signs one time on this interval, and that would be right there. And so my answer would be, and guys, I don't care how you format this, either way, is that my graph is going to hit the x-axis somewhere between these x's, so somewhere between -2 and -1. You may write it like that, or you may write it in interval notation, is that we will have a 0 somewhere on the interval from -2 to -1. So again, let me give you a visual of what's going on. We've got this picture. Over here at -2, we had a point down here at -7, right? -2, -7. And then up at -1, we had a point up here at +2. Since my graph is continuous, I know as I connect those 2 points, it's going to hit my x-axis somewhere in between -2 and -1. That's what's happening, okay? So let's try one from scratch. On this one, yeah. On our next one, I think we'll find a few more throughout, because you need to scan through the entire time to see when it changes signs, because you can have multiple zeros. Oh, I'm so glad you said it that way. No, I'm going to teach you a trick on your calculator. Grab your calculators, okay? No, you are not plugging all those in, because wouldn't that take forever, especially because I made the interval really big on this one, from all the way from -4 up to +4. And I don't want you to sit here forever and plug in all of those numbers. So we're going to do a lot of getting to know our calculators this year to do things like speed up our process. So let's talk about our table. There's your function. We are supposed to go on the interval from -4 to 4. So the numbers we are testing out, -4, -3, -2, -1, 0, 1, 2, 3, 4. I don't really care how you make this table for yourself, vertical or horizontal, does not matter to me. But we need to be able to look side by side of our answers. Okay, while you're getting that set up, I'm going to grab my calculator so that I can show you a way faster way to do this on our calculators. Go type that into your y equals. Okay, in my y equals, I typed in the function x cubed minus 4x plus 2, which is what our equation was. Okay, this first step I'm going to show you, you will probably need to only do once unless you're not using your own calculator and or it gets messed up somehow. Typically it doesn't get messed up, but we're going to go use our table to make a table. And the way we want to check it to see if it's set the right way, everyone, you ready? Hit our second key, and above window where it says table set, that's where we're going right now. So second, window, and you're going to get this little menu. The start does not really matter because we're going to be able to move that around, but make it somewhere close to 0-ish. If it's like at like 100 or something, put it close to 0. Mine's at -5, that's close to 0. What I care about is this next part, delta table. That's how far we're stepping. You want that to be 1. Okay, that means it's going to plug in every one number. Okay, and now let's go look at our table. Hit second again. Table is above graph, so hit second, graph. And you're going to get this nice, beautiful table, and you can arrow up and down, and all it's doing is plugging in those x values to the function we typed in y1. So if I arrow up and down, I can find numbers like if I wanted to plug -9 into my function, that's the answer. We were supposed to test from -4 to 4, so I'm going to arrow this down a little bit. There's my answer for -4, -46. That's my list of answers that I'm going to now go write in my table. So we get what? -46, -13, 2, 5, 2, -1, 2, 17, 50. So if you ever have to evaluate a function for multiple values, now this only really works if we have whole numbers, but if I have multiple values that I need to assess or analyze my function for, use your table. Later I'll show you if it's not whole numbers, another option that we have. Any questions on the table part of it? Okay, so now let's finish out answering the question. It says, between what numbers do we have real zeros? Again, these are the numbers I see, but I really care about their signs. Are they positive or negative numbers? Well, this is a negative, negative, positive, 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 negative, positive, positive, positive. You don't need to mark that at all, but it kind of helps me see. I'm looking for where it switches signs, okay? So as I trace along, that's the same sign, it switches here. So this is going to be one of the places that it's going to cross through my x-axis. Continue going, positive, 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 negative. It switches from a positive to a negative there. And then immediately again here. So you actually have 3 places that this is going to hit your x-axis. And we can again write it as this phrase between -3 and -2. And I write out all of them. Or you can do it, yep, and you can union them too, or just write them next to each other actually, between -3 and -2 if you want to do them in interval notation. Okay? Any questions on that intermediate value theorem? All right, your assignment. Bunch of random numbers here. You are on page 30.